Hello students, today I'll start with the new modules which are related to signal properties, optical properties or optical the fiber characteristics, how if the optical axis propagating through the optical fiber, what are the characteristics we can define, how the light can propagate, what are the impacts are there, this thing I will discuss today. Is there any degradation in the optical light when it is propagating through the fiber? This I will discuss today. Okay. So there are the two kinds of the degradation in case of the optical fiber. One is the signal attenuation, and another is the signal distortion. Normally, here you can see, suppose this is a one kind of the optical signal, sinusoidal optical signal is there, right? So one is signal attenuation, another is the signal distortion. When the signal attenuation is used to happen, so this is the amplitude which is varying with the distance. Okay, it's propagating along the length of the fiber, right? So this is the amplitude of the optical signal. So when it will happen, if the suppose after certain period of time, so the amplitude of the optical signal is decreasing with respect to distance, then this effect is called the signal distortion, the attenuation, signal attenuation. Where at this moment, suppose this is z is equal to 0. At this moment you can see this mass amplitude, so here this suppose z is equal to suppose a. At this moment you can see the amplitude is decreased, so normally it used to decrease exponentially. So this is the signal attenuation, right? So loss of the optical power over a set distance, the fiber lower attenuation will allow more power to reach at this level. So that means if the lower attenuation means the it is not affecting whatever amplitude you are getting at the input side, the same amplitude you are getting at the output side. So this is the lower attenuation. Higher attenuation means so the amplitude is decreased with respect to the distance. Sometimes we need to use the repeater for getting the original signal. So the attenuation is the important factor of the fiber when you want to send the optical signal through the fiber. Next is the signal distortion. So distortion means it's the shape of the, here in case of, you see the shape is not changing. So the amplitude is changing. Okay, but in case of the signal distortion, the shape will change. So this is the one shape. At the input side, that's suppose positive half of the sinusoidal. So now if it reaches at the other side of the optical fiber, you can see the shape is changing like that. So from the narrow pulse width, it's getting the wide pulse width. So this is the signal distortion, or that means the pulse broaden. So there is a broadening of the pulse. So for that, suppose you can say this is a one wave. Suppose you can see this is like that. So if the pulse is broadened, then what will happen? This pulse is broadened, so the next consecutive positive half that will overlap with each other. Two positive half will overlap with each other because each and every pulse are getting overlap, right? So this concept is called the signal distortion. So I hope it is clear. So what are the reasons why the attenuation is happening, or why the signal distortion is happening? This we will discuss in today's class as well as the upcoming lecture. Related to attenuations, there some formulas are there, and we will solve some numerical related to attenuation. Right? So the attenuation, it has some mechanism. Some mechanism, due to some mechanism, the attenuation happened in the optical fiber. One is the absorption, scattering, and the radiative loss. So I'll describe briefly in these three things. Just in one line, I'm telling here. The absorption means suppose when the light is propagating through the fiber, the some portion of the light is absorbed by the material of the fiber. Okay, material of the fiber, or there are the some reasons to for that some portion of the light is getting absorbed by the optical fiber. So due to that, you are not getting the entire power or entire amplitude. Scattering means here also, so instead of suppose it should be propagate like this way, the light, and it should get in the other side of the fiber. So sometimes when it hits the Coat-leading interface. So this is the coat-leading interface. When the light hits the coat-leading interface, so rather uh, following the total internal reflection, it will reflected back in the different direction. So and not entire amount of the light is propagating along the particular direction. So some amount of light are um, directed in the other directions. So this concept is called the scattering. So due to that also attenuation is happen inside the fiber. Next is last one is the bending loss. So bending loss by name also you can see if the fiber, if you bend the fiber, so due to that it's not properly following the total internal reflection, or it is not going in the particular direction. So if there is interface, so again there will be a reflection from the geometry of the fiber. So these are the reasons for getting the attenuation inside the fiber. How can you measure the attenuation of the fiber? So attenuation is an important factor you need to measure. So for it depends on the characteristics of the fiber. So for each and every fiber have some. When you design the fiber, first you need to measure the attenuation constant or attenuation factor of the fiber, so that you can understand how much power is getting absorbed inside the fiber and how much power you will get at the other end of the fiber. So I told that suppose this the amplitude here, the amplitude. So this the z is equal to 0, you are getting this same behavior, same amplitude. But if the z is equal to suppose a, this is the far away from the z is equal to 0 at other end of the fiber. So here you will get the amplitude like this. Okay. Uh, Okay, so here you can see this is suppose z is equal to 0 at this moment. Here it is z is equal to a. So if you pick the peak point of the amplitude signal, you can see it is exponentially decreasing. Okay, so p within bracket z, it is the other side of the optical fiber at z distance. So the maximum power at the z distance. So this is pz. The p 0 is the maximum power at input side, how much power is launching inside the fiber. This is the p naught. So it is exponentially varying e to the power minus alpha p z. Alpha is the coefficient and z along with the length it is decreasing. That's why this is the multiplication factor alpha p and the z, right? So if you do some substitution, you will get this equation alpha p 1 by z ln p naught by p z. And so if this is in the form of the ln, if you want to do in the form of the log, you will get this equation alpha is equal to 10 by z log p naught by pz. So what is the unit of the attenuation? This is dB per kilometer. Okay. So the attenuation, this is one of the factor for on the parameter for optical fiber. So you need to define as a dB per kilometer. Okay, alpha dB per kilometer. So this is the loss happening per kilometer. Okay. So if you remove the dB concept, you can see that the loss will be is equal to, the loss is equal to P input power minus P output power. Okay. In case of the, if you take the dB, then there is a no concept of the, if you take the dB, so instead of pi you have to write as a log pi minus log p out. Okay, the loss in dB is equal to log pi minus log p out. So log pi minus log p out, this is concept of the log of pi by p out, right? So this is the concept log of pi by p out, 10 log. Okay, 10 log. You need to take, if you want to calculate the, if power is there, if you need to calculate. So suppose pi is a 5 milliwatt. You need to convert pi in a dB, so that you have to like as a 10 log 5 milliwatt. Okay, that this power will be converted into dB. Okay, so if you need to convert this concept in the dB, you have to multiply as a 10 log p my minus 10 log p out. So then it will come log p naught by p out, and per kilometer, then the length will come here 10 by z log p naught by p. So this is normally concept loss inside the loss in power. Okay, in the form of the dB. Loss means the initial power and the output power. If you remove the dB, it will be like that. Loss is equal to initial power and the output power. Now I come to the two numerical. Here you can see I have solved this one. So there is this given length of the fiber is 10 kilometer. The launching power, that is the input power, that is 100 microwatt. So I have not explained the question, just I am putting the values. What are the values are there? The power at the fiber output, the output power. Okay, output power will get the 5 microwatt. Calculate the attenuation in dB and attenuation in the dB per kilometer. First, I proceed with the dB per kilometer. You know the formula. The alpha is equal to 10 by Z log P in by P out, right? So the attenuation dB per kilometer is equal to 10 by Z log P in by P out. The Z, you know, the 10 kilometer. Okay, because the unit is dB per kilometer, so the Z is not equal to convert it into the other parameter because it is already in kilometer. And this microwatt cancel out 105 put here, so we'll get the 1.301 dB per kilometer. This is the attenuation per kilometer. And the total attenuation, what will be the total attenuation? So this is, if you divide the attenuation per kilometer with kilometer, you will get the total attenuation, right? The attenuation dB per kilometer into kilometer. Okay, we'll get the total attenuation in dB. So the total kilometer means the length of the fiber. So Z into alpha. Okay. So 1.301 divided by kilometer into 10 kilometer, you will get the 13 dB. This is the total attenuation of the optical fiber. Now, suppose there is another part. So overall signal attenuation for 12 kilometer optical fiber. Calculate the overall signal, not dB per kilometer. You have to calculate the overall signal attenuation for a 12 kilometer optical fiber. The optical fiber has a length of 12 kilometer, right? And not only it has a simple optical fiber which has the 12 kilometer, along with this, this 12 kilometer optical fiber is connected with the splicer. Okay, some joint or connector is there. Using this connector, you made a 12 kilometer optical fiber. So 1 kilometer optical fiber, you join 1 kilometer optical fiber and made it 12 kilometer. How you can understand this one? Because the link using the same fiber splices at 1 kilometer interval. Splicers means the connector at 1 kilometer interval. So if you have the 12 kilometer length, so how many splicers are required with a 1 kilometer interval? So 1 kilometer interval, 11 splicers are required. I hope it is clear. So then you need to make a 12 kilometer optical fiber using the splicer at 1 kilometer interval. So how many splicers are required? 11 splicers are required. You need to put the 11 splicer in between front end and the other side of the optical fiber. So each splicer has some attenuation. It has the 0.5 dB. If total 11 number of splices are there, then how many, what is the attenuation for each splicer? 11 into 0.5, right? 11 into 0.5, because you need the 11 amount of the splicer which has, individual splicer has a 0.5 dB. So if you want to calculate the total attenuation, you need to measure the what is the attenuation per kilometer for a particular fiber and what is the attenuation for the splicer, because the splicers are also required. Okay, so attenuation will come from splicer, that is 11 into 0.5, and for 12 kilometer there is a fiber attenuation, that is 1.30 dB per kilometer. This is the fiber attenuation. The dB per kilometer attenuation is constant for a fiber, either it is 10 kilometer or it is 12 kilometer or 20 kilometer. Overall attenuation will change because of the length of the fiber, right? So then, as you know, the attenuation per dB kilo attenuation is 1.3 dB per kilometer. So then you have to convert this attenuation into total attenuation, multiply by 12 kilometer. So 1.301 into 12 plus 11 into 0.5. This is the total attenuation. If connectors are not there, if only the total 12 kilometer fiber, then only this much is fine. 1 point, you need to multiply the attenuation constant per dB per kilometer with the total length you will get. But along with this, we have the attenuation and connector, and each connector has the 0.5 dB loss. So this is the total attenuation. I think it is clear for all of you. Next is the one part here. It is given that the Z, the length is 12 kilometer. Length is 12 kilometer, loss is 1.5 dB per kilometer. the fiber attenuation loss 1.5 dB per kilometer. So if the output power is 0.3 microwatt, how much minimum launching power is required? Okay. So what are the things are given? The length z is equal to a kilometer is given. The attenuation per dB per kilometer is given alpha 1.5 dB per kilometer. The output power should be 0.3 kilometer 0.3 microwatt. What will be the minimum launching input power? Launching power means it is the input power. So you know the formula, the alpha is equal to 10 by z log p in by p out, right? So if you do some manipulation, instead of alpha z you have to put 1.5, z is equal to, sorry, it will be 12 not 10, sorry, it is 10 not 12. Okay, so it is 10 you will get something. So how much, if you do the manipulation, you will get this much 18.92 microwatt input power. Okay, second question is that the what will be the input power if the uh, loss is 2.5 dB per kilometer. Okay, if the output power is same 0.3 output, you are getting the 0.3 output power, and you know the loss of the fiber at output side, you measure the output power, and you know the loss of the fiber 2.5 kilometer, and length of the fiber also you know. So how much input power was launched inside for this fiber? How can you calculate? Again the same formula. The P in you have to calculate, P out you know 0.3 microwatt, and loss alpha you know, and the length 30 kilometer, everything you know. Okay, so this is the calculation. Okay, length is 12 kilometer. The alpha z into 12 by 10. Here we will get, here also the alpha z into length by 10 is equal to log of p in by p out. 2.5 into 12 length, this is the 10, and you will get the formula 300 microd. If you are giving the 300 microd at input power, input side you are getting 0.3 microd, so much loss is there in that fiber, right? So here this loss is little bit come, because you are getting the 18 microwatt, you are getting 0.3, so both cases losses are there. So in this way also, if you yeah, input side you are taking the input power, you are measuring the input power, and at output side also you are getting the output power, and you are measuring the output power. So you know the input power and output power, you know the length of the fiber, you can also calculate the how much attenuation is there for a particular fiber, right? So by using this concept, you can easily calculate the how much attenuation is there. You can define the characteristics of the fiber. Okay. So there are the some okay. So what I told in the first slide, if you remember, I told that the attenuation happens due to the three reasons: absorption, scattering, and bending loss. So under the absorptions, there are some parameters. What kinds of the absorptions are there? So one is the atomic absorption, extrinsic absorption, intrinsic absorption. Under the intrinsic absorption, you can get the two absorption, the UV region absorption, as well as, or you can tell as electronic absorption. Another is the uh, near infrared absorption. So these reasons, these things I will discuss in the coming lecture. So what is the atomic absorption, extrinsic absorption, intrinsic absorption, and UV region absorption, infrared region absorption? This I will discuss in the coming lecture, right? And followed by I will also discuss what are the reasons for scattering as well as the bending loss, and I will come to the dispersion mechanism. So I hope you liked my video. Please like, share, subscribe my channel, and go through the video again. If you have any question, you can drop the message.